So the last thing we want to look at with regression is how do we determine if we really have a correlation or a linear relationship? And whenever we want to ask a decision or make a decision about something, it usually means we have some kind of inference going on. So we're going to look at inference for regression and correlation. And that inference looks like a hypothesis test. So as always with every hypothesis test, you start off stating your random variables. Then you're going to state your hypothesis. So we're going to do it for the COVID data. So this is going to be an example for the COVID data. And so my random variable was we had the percent of people in a state who wear a mask most or all the time. In public. And that is what is considered our explanatory variable. So that I'm going to call X. And then the other one is the percent of people in a state who knows somebody with symptoms. And that is my response variable. So we're going to call that one Y. Now our hypothesis is whether or not there is a relationship or not. So we have again our HO and our HA. HA is all we want to prove. So we want to show there is a linear relationship. So that would be your HA, because again, HA is always what we're trying to show, what we're trying to show support for, that there is a linear relationship. If we think about correlation or even slope, that would mean your slope is not zero, because a zero slope means there's no relationship, no linear relationship, and because you have a horizontal line. Or if you have zero correlation, that'd mean that there's no correlation. So that would be your HO. So your HO is there is not a linear relationship. Okay, so those are your hypotheses. That's our steps. Our next step is, of course, to state and check your assumptions. So our stating would be that we have a random sample of n pairs is taken. And we are doing these as pairs. You don't have to have pairs, because if you could have multiple variables and you'd have more than just pairs. We're going to call them all just pairs here and see where it's going. And just think of them as just your ordered triplet or quadruplets or whatever you happen to have instead of just ordered pairs. You can expand that. And then, of course, your check would be, and I'm not going to do it for this example yet. We'll go and do the example here in a couple minutes. But your check would be to actually state your sampling process. So describe your sampling process. Your second one is that for every Y value of the independent variable or the explanatory variable, the response variable. So for every value of the response variable, I am saying it backwards now. For every value of your explanatory variable, your independent variable, your explanatory variable, the dependent or response variable is normally distributed. Now, what this means is, if you think about here, you've got some points along here, right? And you're going to have some line here that you think fits this data pretty good. That's your best fitting line or your regression line. What we're going to be looking at here is that for every single point along this line, for every single point along here, for every X value here, you're going to think about drawing a normal curve here. And you want to have each point here along here for every x value, you're going to have a normal curve. Well, notice there's only 1 point here and only 1 point here and no points here. So you can't really do a density plot to check it. You can't look at all those things normally that we use to check it. And so the check we actually do for this is we look to make sure that we do in fact have a linear scatter plot. So scatter plot should be linear, or the point plot. The other one is that your residual plot should be what we call random. And then we're going to do the calculations in R. And we've actually done those calculations. And of course, then you have your conclusion and interpretation. So we're going to go ahead and do it for this example that we've already been starting. Is there really a linear relationship between percent of people in a state who wear masks all or most of the time in public and percentage of people who know someone with the symptoms? So that's really my question. Let's go ahead and tell you we're going to test at the 5% level. And again, your first step would be to state your random variables. Well, I already did that. I'm just going to go copy them because I'm getting tired of writing necessarily, but we've already done that in one step. Oops, back here. So I'm going to go ahead and copy those. And I'm going to paste them over here. So there's that first step. I've stated those. There they are. All right. Your next step, of course, is to state your hypotheses. I've already done that also, but let's just go ahead and state it here. Your HO, well, let's again, I always like to do the HA. I want to know, is there a linear relationship between my two variables? And because I just define them as X and Y, I can actually say between X and Y. I don't need to write them again. This is why mathematicians and statisticians do this. If we're too lazy to write it all again, these days with copy and paste, you can just copy and paste them in there, but using the X and Y helps me. And then my HO is there is not. And I should have said there is, or not is there. It was not a question, it's a statement. So sorry about that. There is a linear relationship. There is not a linear relationship. Between X and Y. All right, now we get to our calculations. Okay, so we're now going to go ahead and go to our calculation step. And our calculation step is what we're going to do in R. Actually, I'm sorry. We do our state and check a random variable, our assumptions. What am I doing? So my first assumption is we had a random sample of 51 pairs of percent of masks and percent of symptoms is taken. So that's the stating. Now I want to check it. Again, this was done by Carnegie Mellon. It was done using Facebook. We're not really sure this was really a random sample, but Carnegie Mellon did feel that it was a fairly good representative sample. So I'm just going to say Carnegie Mellon. Oops, I should not have spelled Carnegie. Carnegie Mellon thinks the sample is representative. All right, so there's that one. The other one is that the populations, we're going to state it. The population of the percent of symptoms. And again, I'm not writing that exactly right. I'm just being a little lazy here. So the percent of symbols for each percent of mask wearing is normally distributed. And so we need to figure out how to do this, and we want to look at the scatter plot first. So the checking is to look at the scatter plot and to look at the residual plot. So we'll go first over to R, and we'll get our GF point plots, scatter plot of the point plots. And we're going to again do our response variable first. So response variable was the percent simp and versus our percent mask. And the data was in the COVID. And again, you should have a title. The title was COVID data. So that'd probably be what it said. I'd probably say COVID-19 data. If you want to, you could put a color in there. So you could actually do color equals, and we could do a color based on location. If you wanted to, you could do that. You could see what's going on. It's not really imperative, but it's useful. So there it is, and there's our graph. So again, I'm going to copy this and paste it in here. And I'll go copy the graph. And again, the way we copy the graph is we go to export. We say we want to save copy to clipboard, and then we right click on it or control click if on a Mac. And then we can go put that in there. And that looks fairly linear to me. It's not perfect. Remember, we don't have a lot of data, but it is fairly good. So I would say this does look linear. Okay, now we need to go graph the residuals. So going back to R, we do need to create the linear model first. If you already did it, it's already there. So we could just go ahead and use the one we already have, but just to make sure you know how to do this again. It's linear out, I call it LM out. You can do anything you want. It's linear model. Then you always start with your response variable, which was the percent symptom, and then you use the percent, your explanatory variable, percent mask. And then make sure you put data equals COVID. And again, all this does is save this. And then we actually want to do a GF point. And we're going to actually put this straight in here. We wanted to create the residuals. We actually want to calculate the residuals for that LM out that we just created. And then we want to tilde that with the percent mask, because we're looking to see if the percent mask is equal to what's happening with our explanatory variable based on these residuals. So you do this as a command. Again, I'm going to go copy that into here just so you can see what we did. And there's what we did. And then I'm going to go copy the graph so we can look at it and talk about what it means to be linear, be random. So copy this to clipboard. And so now this is the residuals. And so basically what you can see here is there actually is a zero line here. Right here, the zero line. So this is your x-axis right there. So applying along that x-axis. And we can see that sometimes residuals are above the axis and sometimes below, because sometimes they're positive and sometimes they're negative. And you want to see, do you see a concerned pattern going on here? I do see 3 points, a bunch of points right here on this line. That just meant they all had the same x value. Again, these all had the same x values. I don't really see any great patterning going on here. I don't see anything I could draw and say there's a relationship going here. So there's no pattern. So since we were linear and there's no pattern, then we can say the y is normally distributed for every x. And from that, we can now go and calculate our calculations. We can now do the calculations. So that's our next step. And so if I go into RStudio again, I've already done it. We're going to do it again. You've actually already done it. You just don't realize you did it. It's summary of your lm.out. And so what we have is, we go copy that. And I'll bring that over here where we are. Okay, so here we have this, and we do actually have everything we need right from here. You just don't realize it. Again, we've already looked at this summary thing before. This gives us our residuals, just a summary of our residuals. This gives us our y equation right here. The standard error, we haven't actually talked about what that is, and we won't get into what that actually is, but that's what that number is. Oops, not that one. But that number right there is your standard error, these two. Then you have this thing called a t-value. That is your test statistic. So that number right there is your test statistic. And then you have a p, PR. PR stands for probability. So there's your p-value. So your t-value is your test statistic. And there's your p-value. But now we have two of them here. We have to figure out which one we actually want. This first row is the intercept. So if you want to test your intercept of it, whatever it is, we don't really need to test that intercept. We actually want to test the slope. So we want to know, remember this coefficient here is the slope. This is the line we want. So our test statistic is t is equal to negative 12.26. And our p-value is 2 times 10 to the negative 16. I want to point out, by the way, that the similar information is down here. This is using something called an F. Fisher was a big researcher and developer of statistics, and F stands for Fisher. It was named after him. It's a different test statistic. It still is kind of the same idea. It's a fairly large number. Again, our t was a fairly far away from 0, so it still means that there's something going on. But more importantly, notice your p-value is exactly the same. So our p-value is the same value. So you can also use this p-value if you want. Now we can get to the conclusion. Our conclusion is that we can reject HO. because we found something unusual. That's again the whole idea behind statistics is, could this have just happened by random chance? Could this information we found just have been done randomly? Or is there something that actually there's evidence that it could have been something more than just random? And because my p-value is so small, this is basically saying the chances of getting this t-value, this test statistic, which means it's the chance of getting this slope, given that there really isn't a linear relationship, is really, really small. It'd be very unlikely that this would happen. And since it's very unlikely, then you reject HO. And if you reject HO, that means you have evidence to show your HA. So that's your interpretation. The whole idea of the whole HO is just to have something to test with, to assume is true. And then when you prove that, then when you have reject HO, you know, oh, well, I can reject that. That can't be true, which means my HA must have some evidence. So there is evidence that there is a linear relationship.